So in our previous lesson, we looked at dynamic equilibrium. That's the case when the forward reaction equals the rate of the forward reaction is the same as the rate of the reverse reaction. Sometimes this is not always the case. Sometimes the rates are different. This is where equilibrium constants come in. So an equilibrium constant is a measure of where the equilibrium lies, whether it favors the products or the reactants. So each equilibrium reaction has an equilibrium constant Kc. And this equilibrium constant is constant at a certain temperature. So looking at a reaction of A moles of A plus B moles of B giving C moles of C and D moles of D, then the equilibrium constant will be a ratio of the amount of products, or concentration of the products, divided by the concentration of the reactants. So for our reaction, it will be the concentration of C to the power of the number of moles of C times the concentration of D times the number of moles of D divided by the concentration of A times the number of moles of A times the concentration of B times the number of moles of B. Those square brackets illustrate that it's a concentration. Okay, so now considering what we just seen in the last slide, write the equilibrium expressions for the following three reactions. So I'll pause the video now, go and write something on a piece of paper and see if you're correct. I'll be back in about 5 seconds. Okay, so welcome back. So hopefully you got the following. We're just going to go through this. So Kc for A will be Kc will equal the concentration, remember it's products over reactants. So it's going to be N, oh dear, just make sure we get this right, N2 and H2, and the superscript will be 3 because we've got 3 moles of hydrogen, divided by the concentration of ammonia squared because you've got 2 ammonias. So hopefully you got that one right. The next one be Kc will equal the concentration of ammonia again, this time to the power of 4, and it's divided by the concentration of nitrogen squared times the concentration of hydrogen to the power of 6. So concentration of hydrogen has a big effect on that reaction quite clearly, to the power of 6. Okay, and for the final one, the Kc for this particular acid-base kind of reaction will be the concentration of CH3 COO-, the acetate, times the concentration of the hydronium H3O+, divided by the concentration of CH3 COOH, the acetic acid, times the concentration of water. So hopefully you got those all correct. So in terms of equilibrium constants, you need to indicate the number indicates the extent to which their equilibrium favors either the products or the reactants. If K is very large, like much larger than 1, for example 1 million or 1 times 10 to the 6, then the equilibrium will be, there will be far more products than reactants. Because remember, it's going to be products over reactants. So if products are really big and reactants are really small, the Kc is going to be very large. So for example, here we have a reaction, hydrogen plus chlorine in equilibrium to give 2 hydrochloric gaseous molecules. The Kc is 4 times 10 to the 31 at 300 degrees Celsius, clearly indicating that is a very large number, that a lot of hydrochloric gas is formed and there's virtually none of the reactant hydrogen and chlorine left at that particular temperature. But if the Kc is very small, much less than 1, for example, like 1 times 10 to the negative 6, then there are far more reactants than products. Because again, remember that Kc equals the concentration of products over reactants. So if this number is really small and this number is really large, then it's going to end up that the Kc is going to be really small as well. So the example which you actually did an equation for of methanoic acid and water dissociating to become methanoate and hydronium. The Kc is 1 times 10 to the negative 5 at 25 degrees Celsius. So that means there is very few ethanoic acid molecules present. Sorry, ethanoic, not methanoic. My bad. Ethanoic acid molecules present to split up into hydrogen and ethanoate ions. So that means the reaction favors the reactant side. So there's lots of ethanoic acid around, but not much of the hydronium. That's why it's a weak acid. So for our final part of the lesson, let's just look at calculating a value for Kc and working out whether it favours the reactants or the products. So here's a reaction. Hydrogen plus iodine giving 2-hydroiodic acid. Well, it's actually in gas form, so 2-hydroiodic gas. So you've got this mixture at 491 degrees Celsius, quite warm in a sealed flask, and it's equilibrium. The concentration of hydrogen is given at 2.5 times 10 to the negative 2 moles per decimeters cubed. Iodine's 2.5 times 10 to the negative 2 moles per decimeters cubed, and the hydrogen iodide that was formed at equilibrium is 1.71 times 10 to the negative 1 decimeters cubed. So your job in the next 5 minutes is to calculate Kc. You have the information, so I'll pause the video now, try and work it out on a piece of paper, come back and see if you're on the right track. Okay, so welcome back. So here's the answer. So Kc equals the concentration of Hi squared, all squared, divided by the concentration of hydrogen times the concentration of iodine. So you plug the numbers in and you get this number here, 46.8. So what that tells me, because it's 46.8, it's greater than 1. So it says to me that the products are in higher concentration or favoured compared to the reactants. Okay, which makes sense. So that means that this reaction is going to favour the products. So I think that's enough for today's lesson. So if you got that correct, all good. If you didn't, maybe it's time to go over your notes, see what you did wrong, and see if you can see where you made your mistake so you won't make a mistake. No, same mistake next time.